I'm fortunate enough to tour around and talk about this stuff in various countries around the world. I usually start with a joke about football, but there's no joking about football between England and Germany because you beat us too often. So I apologise that I'm delivering this talk in English to a room full of German speakers. My bad. So let's start. I'd like to talk about the reason why I think continuous delivery is important and some fundamentals about how it works. And part of the starting point of this is, sorry. Okay. Can you hear me okay? It sounds echoey to me, so I thought it was working. Okay, so part of the starting point for this is it's my assumption that on the whole we don't do software very well. And so I want to start off by trying to convince you of that. So if you look at data about software projects, you probably should be skeptical about the scientific validity of these kinds of project studies. But nevertheless, it's probably the best that we got. It's really very hard to set up a strictly controlled experiment for project success. And these surveys tend to say consistently negative things about the ways in which projects work. This last one is kind of terrifying in an amusing way. It would be amusing if it wasn't quite so terrifying. 17% of large software projects go so badly that they threaten the existence of the organisation that undertook them. That's quite a frightening sort of statistic. I think that if software development, software projects were normal things, there should be a normal distribution. As many projects should finish ahead of schedule, under budget, and delight their users, as be over budget, behind schedule, and generally disappointing their users. But I don't think, I can see that people are finding that amusing, quite rightly so, again in a macabre sort of way, and that's because we've come to assume that's what's normal for software projects. We assume that our software projects will overrun, deliver things that people don't really want, have lots of bugs in them, and so on. So I would argue that software development is kind of suboptimal as a process. But I also think there's signs of hope. I think over the last few years we've discovered ways that actually work. We've started gathering data that suggests that we're correct. For the first time, we have numbers that say there are approaches to software development that can give organizations that practice them a bottom line advantage. I'm going to talk more about that. So let's kind of start. So what have we done in terms of process? What have we done? We've gone and looked at other industries, and we've kind of picked up. We've tried things that we've seen there. We've looked at waterfall models, V models. We've tried subdividing complex problems into smaller problems, and we've ended up building siloed organizations where we hand over things through different stages. We've tried doing more iterative approaches to software development. We've tried things like Scrum to help us with the project management. We've tried things like extreme programming for the engineering disciplines. We've tried hiring really smart people and putting them in a corner, and we've tried hiring teams of young smart people because they're a bit cheaper. And we've tried hiring young smart people in foreign countries because they're a bit cheaper. Some of these things help, and some of them not so much. I want to show you one thing that I think has not helped quite so much. This is a paper from 1970. This is the paper from 1970 that introduced the idea of waterfall as a software development process. So this was written by Dr. Winston Royce for a symposium sponsored by the IEEE. And This is the diagram. Can I just have a show of hands? Has everybody seen this diagram before? Yeah, that's kind of what I guessed. You can imagine reading the paper and seeing this diagram and thinking, oh, that's okay, I can remember that. I'm going to go home and I'm going to draw that on a whiteboard or write it in a document to explain to my team what I've just read. Okay. It's kind of missing the next paragraph. So this is the next paragraph in the document, which I've expanded for you. And it says, the implementation described above is risky and invites failure. The testing phase, which occurs at the end of the development cycle, is the first event for which timing, storage, input-output transfers, etc. are experienced as opposed to analysed. These phenomena are not precisely analysable. So the document that introduced to our industry the idea of waterfall development was saying, don't do waterfall development. Apparently, Dr. Royce spent much of the rest of his career saying, that's not what I meant. As I said, it's a nice, simple picture, and you can understand why people preferred it to this, which comes later in the document, which is what Dr. Royce was recommending. It's harder to go back to your organisation and draw this on a whiteboard from memory, right? But if you read the paper and if you look at the detail, it's interesting. It says up here that we should be using testing as part of our development approach. Intimately involved in our development process. It says here that we should actively introduce feedback cycles from testing into system design, from system design into requirements. What a generous take of this paper is that this is kind of a 1970s view, given the benefit of 2020 hindsight. This is a 1970s view of what agile development would look like. And this is what Dr. Royce was actually recommending. I want to show you a little animation. So this is a quayside in the west of Ireland. I went and spoke at a conference there last year, and somebody came and said, that's my cousin. But you can see that something bad has happened, and there's a car has driven off the quayside and has fallen into the water. So what do you do when that happens? Well, you go and get a crane. That seems fairly straightforward. What do you do now? You get a bigger crane. You can see where this is going, can't you? Einstein said that the definition of insanity is doing the same thing over and over again and expecting different results. So if our software development processes don't really work, we should try something else. I would argue we should try anything else and figure out what really does work. So let's go back to first principles and think about what it is that we're looking for from software development. And without too much fear of contradiction, I think that every organization that creates software wants this. They want to have an idea, they want to get that idea in the form of working software into the hands of their users, and they want to figure out what their users make of that idea. I think that's what, we're all software professionals in this room. This is what we are employed to do. This is our job. Fundamentally, nothing else matters. This is what we're supposed to be doing. Getting software, working software into the hands of our users and figuring out what they make of it. So I think we should optimize for that. I think that we should, we are people whose career is solving hard problems. This is a hard problem. Let's start applying the sorts of reasoning that we apply to other problems to our own software development process. So I think we should look to start off by optimizing that process. I want to ask you a question. So, what's the most successful invention in human history? And here are some pictures to steer you down the wrong road. I pressed the button too soon. So I would argue that science is the greatest invention in human history. Without much fear of argument, if you look at the record of human history, by almost any measure, if you look at the amount of energy that we wield, the number of facts that we deal with, the distances that we travel, the resources that we consume, by almost any measure, the whole of human history, about 200,000 years since Homo sapiens evolved, has been a flat line. And about 200 years ago, that flat line started to curve up, and through the 20th century and now the 21st century, it goes asymptotic, it goes vertical. It's an exponential growth by almost any measure. And that's almost entirely down to the Age of Enlightenment and the introduction of scientific reasoning to solve hard problems. The people 200,000 years ago were no different to us. They had the same capacity, the same levels of ingenuity, and yet they hadn't come up with a method for solving hard problems that was durable. We have. So I am not talking about Large Hadron Colliders, gravitational wave detectors, modern medicine, space shuttles. I'm talking about this. I'm talking about the simple four-step process that is the scientific method. So, like all good presenters, I went and looked it up on Wikipedia, and it says the scientific method is, first you characterize the problem. You make a guess based on experience and observation from what you see. Second, you propose a hypothesis. You propose an explanation that might be able to describe what's going on, what it is that you're observing. Third, you make a prediction based on the hypothesis. And fourth, you carry out a test to evaluate that prediction. And then you repeat. I think that software development is one of the more difficult things that human beings undertake. I have a friend who used to be a theoretical physicist, and she switched to being software because she thought it would be more challenging. I think it probably earns more money as well, but it's a genuinely difficult problem. Software is enormously complex. My German is very bad, but I think that you were saying that there are 150 million lines of code in a car. Okay, there are 6 million pieces in a Jumbo 747. The level of complexity of the stuff that we create and work in every day is just beyond human experience. It's also intensely fragile. There's very little in human experience where you can have a comma out of place and that's dramatically going to change the results. But we all know that that's true of our stuff. So shouldn't we be applying our strongest problem-solving technique to our hard problem of developing software? I think we should be taking a more rational, more scientific approach, a more hypothesis-driven approach to the things that we do. So let's dig into this a little bit more. So let's look at what works. This is some data from another one of those project surveys. This has been collected by the Standish Group, and they've been collecting data like this for at least a decade, probably a bit longer than that, probably about 15 years. And it's generally consistently depressing in terms of what they say about project success. Waterfall projects on the whole are only 14% are successful. By successful, they mean on time, on budget, and delivering what the users want. Remember my normal curve. And agile projects are closer to half, so you're getting a bit closer to a normal distribution there, so with 42%, but still that's pretty depressing. Some people think that is too depressing, and one of those people is Scott Ambler, who's also been collecting data on project statistics, and this is my organisation of his data. The top line is are kind of iterative approaches. You can think of them as more empirical approaches to development where you've got time to learn and react. The bottom line are more traditional planned approaches. It slightly made me laugh the first time I saw this data that if you make up your development process on the spot, it's slightly more effective than waterfall. That's just my weird sense of humour, I suppose. But lean is kind of stands out as one of the better things. So let's look at what that's about. It's really not very surprising given my argument that lean stands out. Lean is the child of the thinking of Edwards Deming at the end of the Second World War, who went to Japan and revolutionized their production industries and taught them how to think more rationally about problem solving. And The way that he did that was to kind of do what I've just suggested. He went back to first principles, looked at what the scientific method was, and figured out how to apply the scientific method to production engineering. He came up with an idea called Plan, Do, Study, Act, and various other things, but that were a direct lift of the scientific method that I was talking about. But some of the things the modern lean thinking talks about, we want to deliver quickly. We want to deliver things so that we have the opportunity to learn, adapt, change, reflect, and move on. If we want to do that, we want to be able to build quality in. We want to be able to have deterministic results. We don't want to be able to go back and be fixing lots of problems that we introduced earlier up in the chain, because that's going to slow us down. It's going to compromise our ability to deliver quickly. If we're busy fixing loads of bugs once it gets into production, it means that we haven't got the chance to learn from production and to get new changes out quickly. We've got to look at the whole process. It's no good spending months optimizing to shave 5 minutes off your build if it takes you 5 weeks to make a decision about which story to play. That's a misuse of resources. We need to look at the whole process and figure out how to make the whole thing better. Lean talks a lot about waste, and there are different forms of waste. We can think about unnecessary variations. If we're doing the same thing in different ways, that's probably a form of waste. It means that every time we come to, is it this way or that way? I once worked on a project that had 7 different persistence mechanisms for writing changes into relational databases. The only reason for that was because somebody thought, I don't like those other persistence mechanisms, I'm going to write a new one. Which is okay, but then you throw away the old one. But they didn't do that part. Overburden is an interesting one. People are just as subject to maths and queuing theory as queues are. So if you put too much work into a team, they will spend so much time coping with the overload that they will do less work. The maths of queuing theory and experience with teams suggests that you want, and Lean talks about this in some detail, you want to try and manage the working process, and you want to be able to working at roughly 70% of the total capacity of the team, because you want to allow enough space in the team for them to do work that makes them more efficient. That's the highest value work that they can do, is doing work to make them more efficient. And I'm going to talk some more about that later. Wasteful activities. Basically, it's not enough to do a really good job. You've got to know what to do and then do a really good job. Doing a wonderful job of writing a feature that nobody ever uses is not high value. So we need to identify the things that people want and figure out how to deliver those quickly and efficiently to people. Modern lean practitioners talk about you optimize. If you want to deliver at the highest rate, the way to the slightly weird way to do that is to not focus on delivery. What you focus on is you focus on learning. The team's objective is to learn, and if you prioritize learning over all else, you will get the highest levels of delivery. That's part of the lean mantra. And last of all, we need to decide later. We want to make decisions at the point when we have the best information. If you make all of the important decisions at the beginning of your project, you're making the decisions at the point when you know the least that you will ever know about the project. If we defer decisions until the last responsible moment, which my wife tells me is moments ahead of the first irresponsible moment, but if you make decisions at the last responsible moment, then we're going to have the best information to make that decision, and so hopefully that means that we're going to make a higher quality decision. And last of all, we've got to empower the team. We want the people that cause a problem to perceive the problem, because they're going to be the people that are best placed to fix the problem. And so working in a way to ensure that that takes place is all part of this. So what are we really talking about? So the more that I think about this is that what we're really talking about is establishing feedback loops. This is really what Agile is all about, Lean is all about, and certainly what continuous delivery is all about. We're trying to concretely, consciously establish feedback loops that allow us to learn, adapt, and change as we move forwards. And at the outside of this picture, there's the feedback loop I've already mentioned. We want to get an idea into the hands of our users, figure out what our users make of the idea, and deploy that in form of working software to our users, and then figure out what our users make of the idea. At the inside is probably something like a test-driven development loop. We want to write a test, see it fail, write some code to make it pass, refactor, commit, move on. And there are once you start thinking like this, you start seeing these feedback loops everywhere. And more importantly, once you start thinking like this, everything that you do, you want to figure out where's the feedback loop? How can I learn from this? How do I get answers? How do I know that this was a good decision? How do I know that this was a good technology choice? Whatever it might be. As you can probably tell from my talk so far, I'm a bit of a popular science nerd. And this is one of my heroes. This is Richard Feynman. Richard Feynman was a Nobel Prize-winning physicist, and I think without too much fear of contradiction, he's probably one of the finest minds of the 20th century. A genuine first-class genius. He won his Nobel Prize for inventing something called quantum electrodynamics, which is the most accurate predictive tool that humanity has ever come across. By 2 or 3 orders of magnitude, it's better than general relativity. It's a stunning piece of work, a genuine genius. And he said, it doesn't matter how intelligent you are, and this is Feynman talking, if you guess, and that guess cannot be backed by experimental evidence, it's still a guess. So we need to find ways of getting past the guesses. A lot of my experience has been that a lot of what we do as a normal part of working in software development is based on guesses. I know what the users want. They want this feature. Let's go and build this feature. I know what causes that bug. It's this thing. Let's go and fix that thing and see if the bug goes away. We do this thing all of the time. I know what's going to make our system scalable. Let's build this. Let's use my favorite new technology that I can put on my CV, and then we can write this thing and we'll deliver it, and I'm sure it will scale. It doesn't really work like that. We need to look at this from an experimental idea. So instead of doing that, we need to figure out how can we see if this idea is good in the hands of our users? How can we tell that this technology is going to work for us? How do we know that this is going to scale? We want to measure things. We want to try things out. We want to carry out the experiments. I want to do a little sidebar, a little story about being experimental. And my wife says that I'm a serial nerd. I'm a nerd across lots of different fields. I'm a nerd about aeroplanes. I'm a nerd about the space program. I'm a nerd about computers. And I'm just a nerd, I suppose. So I want to talk about one of my other favorite things, which is the Apollo space program. In 1961, JFK came to Congress and said, I believe that this nation should commit itself to putting a man on the moon and returning him safely within 10 years. And all of the people in NASA went, because they hadn't got a clue how to do any of this. So, as Scott Ambler said last week in a conference, this is the most expensive story ever written. A single line requirement that costs billions. So let's just think about that. So Kennedy's just defined this goal. He's just defined a purpose for NASA. He's given them this vision of what we're going to do, and nobody knows how to do this. So here are the things that NASA didn't know how to do at this point. At this point in history, Alan Shepard, the first American astronaut, it's about 2 weeks after he'd just done his first suborbital flight, which went to about 50 or 60 miles. Yuri Gagarin had orbited, and the Russians had Sputnik, but the Americans really got nothing. I think they got a couple of satellites up, but they were really nowhere in terms of space exploration at this point. They didn't know about multi-stage rockets. They didn't know how to do that. They didn't know. Nobody had docked 2 space vehicles. They didn't know about how the vehicle should land on the moon, or how they should return people safely to the Earth, or any of this stuff. They hadn't got a clue. So where do you start when you've got a problem on that scale? And sure, you can think about, if you're anything like me, you kind of make an assumption that NASA will have these detailed plans and documents, and to an extent they did. These are photographs of real NASA planning documents. But fundamentally behind those is this idea of the purpose, the vision that's been established for what they're trying to achieve. So let's dig into that a little bit more and see where it comes. So here's a picture of the Earth-Moon system. This is kind of a classic kids' school book sort of picture. Unfortunately, it's not even close to the truth. This is a picture of the Earth-Moon system that's closer to scale. At this point in history, no human artifact had been more than 1 pixel away from the Earth in this picture. Just pause to think about that for a moment. So now you've got 10 years to put a man on the moon and bring him safely back. So what's the experiment? I know. Let's put some astronauts in a spaceship and send them to the moon and see if they come back. Yeah, no, that's not great. That's not a great first experiment. I know. We don't need the astronauts. Let's just have a spaceship and send it to the moon and see if it comes back. Yeah, no, that's still not the simplest experiment. So we don't have to bring them back straight away. You know, at the moment, our problem is getting things into orbit and then getting to the moon. So let's launch a spaceship and send it to the moon and land it on the moon. Yeah, okay. It's not the simplest experiment that could possibly work, though. What's a landing mean? Spaceship doesn't have to survive the landing for us to learn. Okay. So let's take a spaceship and fire it at the moon and see if we can hit the moon. That's what this program was about. This is called the Ranger series, and this is spaceships as bullets shot at the moon to see if anybody could hit the moon. So how did that experiment go? So Ranger 1, the launch vehicle blew up on the pad. Ranger 2, the launch vehicle blew up on the pad. Ranger 3, they pushed the mission objective. So the first two were only supposed to get the thing into orbit, but they pushed on with the mission objectives now because they're getting behind time. I think we're all familiar with that kind of thought. So Ranger 3 actually made it into orbit, but missed the moon. Ranger 4 made it into orbit around the Earth, did the deorbit burn, headed off towards the moon, and all of the telemetry systems, all of the spaceship just died. All of the systems at that point failed. So they managed to track it. They saw that it hit the moon, but they had no data. Ranger 5 missed. Ranger 6, it all worked, except the cameras failed just before it hit the moon. So they got all the telemetry, they've been able to track it from outside, and so they got some data, they learned some things, but they didn't have any pictures. Ranger 7 worked. Ranger 8 worked. Ranger 9 worked. So for NASA, so at this point, at least in the Western world, this was the biggest project that was going, and basically NASA had unlimited resources. They could recruit the best minds in the world the best engineering minds in the world to go and help. And at this point, what do? They turn to using an experimental technique because clearly they don't know how to do it. If they just shot the astronauts off and killed the astronauts, that wouldn't have worked. That wouldn't, very, very quickly, the funding would have dried up. I want to show you another little bit on experimenting before we move on. So has anybody seen this before, the Marshmallow Challenge? Okay, this is a psychology experiment that's been carried out across the world with different groups of people. And the objective is that you have 20 sticks of spaghetti, a meter of sticky tape, a meter of string, and a marshmallow. And the job is to build the tallest freestanding tower that will support a marshmallow on the top. And you get, I've carried this out in training courses. It's a lot of fun. And you get all sorts of wonderful constructions that come out of this when you carry out this experiment. There are some wonderful things. But the really interesting stuff is when you look at the data. When you look at what happens. So first of all, the tallest I'm sorry, it's in imperial, because it's American. This is an American picture, so 20 inches is the average. The tallest line is from architects and engineers, and you kind of expect that. They have specialist training, they understand structures, they're going to have a good idea about how to build a tall tower from lightweight materials. You'd hope they'd be able to do that kind of thing well. The next tallest is interesting. So I'm going to go to the other one first. So CEOs, if you get a bunch of CEOs together, they do slightly better than average. What's really intriguing, though, if you get a bunch of CEOs and a couple of admin type people, support people, they do better. So what's going on there? Well, what nearly all adults do when they're carrying out this exercise is that they spend the first few minutes of the exercise doing the social politics of the situation. So who's the smartest here? Who's going to come up with the good ideas? Who's the doer? Who's the person that's going to take orders and go and work? Who's the person that can sit back and kind of direct things from a distance and drink the coffee? When you have a bunch of CEOs doing this, they tend to argue a lot. If you have an admin assistant, they facilitate, and that process goes more quickly, so they get on to doing things more quickly. The thing that's fascinating, though, is the middle one. Kindergarten children outperform lawyers, business school students, and the average. Now, what most adult groups do is they do the politics, and then they come up with a plan. Let's build a structure like this. Okay, you go away and build the footings. I'll go away and build this bit. We'll glue them. We'll come back and we'll glue them together at the end. And then they'll all go away and they'll start working. And they build all this complex structure. They put the marshmallow on the top, which is surprisingly heavier than you might think with all that sugar in it. And it falls over. What the kindergarten children do is that they build 3 legs and put the marshmallow on the top, and they go, yay! And then they raise that up a level, and then they go, yay! And then they raise it up a bit more, and they go, yay! They're carrying out just pure experimentation. They don't have any background, they don't have any learning, they don't have any deep understanding about how to do things. They just experiment, and when they do that, that is better than just the average. So yes, if you've got expert understanding of a problem, then you can outperform the kindergarten children. Otherwise, not so much. Has everybody seen this before? The idea is which is the biggest orange dot, the one on the right or the one on the left? Can I have a show of hands for the one on the right? Okay, show of hands for the one on the left. Show of hands for people that think they're both the same. Okay, how could we possibly find out? We could carry out an experiment. Okay? Has anybody seen this one before? Okay. Which is the longer line? So is the one on the left the longer line? Show of hands? No. One on the right? Is that the longer line? Ooh. Anybody think they're both the same? No, I lied. I cheated. We must carry out the experiments. We are not good enough observers. We are not smart enough to be able to do this without experiments. If we can't do this for measuring lines, what about the software that we write? I'm going to show you something else. So I'm going to show you 2 calculations. My bet is that your experience of those 2 calculations was fundamentally different. The first one, the answer to that calculation will have been presented to your conscious mind probably before your conscious mind perceived that I'd put the calculation up there. It will happen in about 15 milliseconds based on psychology research, and conscious thought happens in the scale of about 300 milliseconds. So this will have just recognized that calculation and given you the answer before you knew that the calculation was there. The second one, my guess is that what happened was probably something like, Dave's just shown me a calculation. Do I know the answer to this? No, I don't. Can I be bothered to work it out? No, I can't. And it will have been dramatically slower. This is the difference between what neuropsychologists call system 1 and system 2 thinking. The first one is pure habit and reaction, and the second one is what we think of as conscious rational thinking. And the trouble is, if you do sorry, I have another experiment first. I will tell you the next bit in a minute. So, could everybody fold their arms, please? Okay, now do it the other way around. It feels weird, doesn't it? It feels strange. That too is the difference between System 1 and System 2 thinking. The first one, we've just by habit, we've learned a way of doing it, and so we've programmed our brain, our neuroplastic brain, to just do that automatically. It requires no conscious thought. The second one, you don't do that very often. And so you have to, how does that work? The wonderful thing is if you put people in fMRI scanners while they're doing this kind of task, you get really radically different pictures. The first one is the System 1 thinking. This is the habitual instinctive reaction. This requires there is no engagement of our consciousness in this kind of thinking, and it's dramatically cheap. The second one is what we think of as rational thought, and it is dramatically expensive, not just in terms of the amount of energy that we are burning in our brain. We are literally burning more calories with System 2 thinking than we are with System 1, but also in time. The first one happens in about 15 milliseconds, the second one happens in about 300 milliseconds. It's dramatically slow. We are programmed to avoid rational thought because it's expensive. It burns more calories. By default, as a human being, our preference is just to guess. So if we want to not guess, we've got to work at it. It's literally hard work. And the downsides to this is that we're subject to all of these common psychological fallacies. We fool ourselves all of the times. And as Feynman says, and we're the easiest people to fool. So science is our approach to avoiding fooling ourselves. Oops, sorry. So I've beaten you over the head about being experimental. It's my argument that if you take an empirical, experimental approach to software development and you use this, the idea of cycle time, as a benchmark, a measurement, and you optimize for this, you will drive out all of lean thinking, all of DevOps, all of agile thinking, all of continuous delivery as an inevitable consequence. So what's cycle time about? Cycle time is a measure of your process, your software development process. And if you think about making the simplest change that you can imagine going into production and doing all of the normal steps that you would do to understand the need for this thing and decide whether it was a good idea and to prioritize it and to develop it and to test it and to validate it and to deploy it. If you do all of those things, how long would it take you to make that change into production? And I'm going to show you cycle times from two organizations in which I worked. The first one was a bank in the UK, and this was a relatively simple project, but their cycle time, was 103 days. They couldn't make a single change to their systems in production in under 103 days. If somebody comes to me after 103 days and says, Dave, you just broken production, I'm going to say, no, I was on holiday that week. It wasn't me, can't possibly have been me. What was I doing then? I can't remember. If somebody comes to me after 103 days, then it might not have been me, because it might have been me and your change and somebody else's change, and it might be the intersection of all of those things. It means that we've now not only have we forgotten what it was that we were doing 103 days ago, but we've also got a more complex problem, because we've got to figure out which of all of the complex changes that we put together is responsible for the failure that we're seeing. The second cycle time is from a project that was in the order of 15 to 20 times more complex than the first project. This was building a low latency trading exchange and all of it, and all of the external communications, all of the regulatory stuff, all of the high performance pieces. We built our own messaging system, all of it. And the cycle time for this was 57 minutes. Now, I'm slightly cheating because the second one is not entirely mappable to the first one, and there are some good reasons for that, but if you don't trust me, the equivalent in the first one is 64 days. The perfect. There were some other reasons why I think that this is a fair representation to 103, but 64 days is certainly mappable one-to-one. So for this project, we could make any change to our software system and evaluate it in 57 minutes. We once decided we didn't like the commercial deal that we had with our relational database vendor, and we switched out the relational database. We made the changes to the code that were necessary. We ran those changes through our deployment pipeline and evaluated the change, and it came back with some bugs. It came back with some problems. We fixed those problems. We ran it through the deployment pipeline again. It was all good. It went live into production the next day. I've worked in places where that alone would have been a 6-month project. Cycle time is a wonderful thing. It's not very often that we have a metric that that drives all of the right behaviors. Cycle time, I believe, is one. If you work to optimize your cycle time, and really fundamentally what we're talking about by doing that is optimizing from having an idea to getting that idea into the hands of our users and figuring out what they make of it. If we optimize for that, then you can't have a cycle time of 57 minutes if you've got big divisions between your teams, because the handovers will kill you. You can't have a cycle time of 57 minutes if you don't have a good story of automated testing. You can't have, unless you want to release lots of bugs into production, I suppose. You can't have a cycle time of 57 minutes if you don't have a great story on configuration management, automation. You can't have a cycle time if you don't have small cohesive teams. You can't have a cycle time of 57 minutes if you don't have kind of a good stance on DevOps and working together. It pulls all of these ways of working together and gives you a measuring stick that allows you to drive good behaviors. By doing things more frequently, it shines a light on the things that we're not very good at and makes us fix those problems. So what's continuous delivery about? So the name comes from the Agile Manifesto. And has everybody read the Agile Manifesto? Cool. Those of you that haven't, I recommend that you do. There's some really good stuff in there. And most people read the first page about people over process and all that sort of stuff with some really great stuff. But there's a second page which is about the 12 principles. And our highest priority is the early and continuous delivery of valuable software. That's what we're in the game for. That's our jobs. That's what we do. It's kind of like the logical extension of continuous integration. If you're a build team and you're building stuff and you're kind of figuring out what works and what doesn't and making changes, then that's great. And so we just want to extrapolate that further. So we want to go a bit more upstream, so we include our thinking about the requirements a little bit and executable specifications and things like that. A little bit more downstream, we want to go into the automation of deployment mechanisms and configuration and those sorts of things. From idea, valuable software into the hands of our users. I like to think of it as a holistic approach to software development. This is not about just the build. It's not just about automating your deployment. It's not just about writing tests. It's about the whole process. It's about optimizing the whole process. And the organizations that embrace this change quite dramatically in order to make this work. I would argue for the better. A good mental model for this is if you imagine every time you make a change, any change that's destined for production, you're giving birth to a release candidate. And the job of our continuous delivery system, mechanism, is to prove that that release candidate is not fit to make it into production. That kind of sounds backwards, right? But this is Karl Popper's idea of falsifiability. We can never have enough tests to prove that our software is good. But as soon as one test fails, we know that it's not good and therefore we can't release it. So we build mechanisms into our continuous delivery system that allow us to run tests, and if one test fails, we say that's not good enough, we won't release it. We'll go back and we'll find out why that test failed and fix that problem. And finished means released into production. Actually, no. This list is taken from the continuous delivery book, and this is one of the things I would change. Finished means in the hands of users delivering value. Our responsibility is not finished until that's the case, until it's in the hands of users and delivering value. So let's look at some of the principles of continuous delivery. We want to create a repeatable, reliable process for releasing software. If we want it to be repeatable and reliable, on the whole, that's going to eliminate us. Human beings are not repeatable and reliable. We're wonderful at lots of things, but repeatability and reliability aren't two of them. If we want it to be repeatable and reliable, we need to automate nearly everything. We want to use the computers for what the computers are good at, use us for what we're good at. If we want to automate nearly everything, we've got to keep nearly everything under version control, because we need our systems to be deterministic. And one of the mantras of continuous delivery, if something hurts, if it's difficult, if it's complex, if it's worrying, do it more often, because that shines a light on the process. If your release process is scary and you're releasing once every 6 months, the worst thing that you can possibly do is to start saying, oh, this is really bad, let's start releasing once every 12 months. I guarantee you it's going to be more than twice as bad. If you're releasing every 6 months and you want to improve, start releasing every 3 months, every month, every week, every day, every 57 minutes. Drive it down. Use the cycle time and optimize your whole process to allow for early and quick and rapid delivery. You don't have to push the changes out every 57 minutes, but you need to work in a way that every time a cycle successfully completes, you're happy to release that thing into production. And then you can make the decision when you release it into production. That's a separate choice. If we want all of our automation to work and our configuration managed to work, our systems need to be deterministic. We want them to give repeatable results every time we deploy them, every time we test them. And so we need to be focusing on the quality. We also don't want to be going in and fixing problems late in the process, because that's expensive. We want to find problems as early as we possibly can and fix them as quickly as we can, because that's the cheapest, most effective and efficient way of doing that. Done means in the hands of users delivering value. Modern organizations are software organizations, and software as a disruptive force is driving what's happening in the world. So everybody's interested in the changes that we are creating and that are flowing through our development process. So we need to work in ways that are transparent. We need to have tools and mechanisms and processes that allow anybody to understand where we are in the way we work. So we need to have requirements that are understandable to human beings, not just technical people. We need to be able to plan those and make changes visible as they flow through the development process, so you can see where we are at any given point. That's just as useful for us technologists as it is for people in the rest of the organization. But we need to think about that. We need to not just supply all of the information that we have in a hard to understand form, but identifying where the high value bits are and crunching the information down. So the classic thing is kind of the X unit thing of you have a test failure reported as a red blob or a green blob. It's just a simple, obvious picture of what's going on. It used to be that unit test frameworks would just report a big list of complex results that you had to wade through and figure out what was good and what was bad. And finally, this is not the kind of change where you can go and buy a product off a shelf or hire a consultant like me to come and tell you, or go on a training course or read a book and just do it and then you're done. It's not like that. This is radical. This is a radical change in the way in which we approach software development. I'm going to provide you with some information later that I hope will convince you that we change the economics of software development. And remember what Einstein said, we can't carry on doing the same thing and expect different results. So we need to work in different ways if we want this to work. And part of that is applying the skeptical mind, another lesson we learn from science, and being skeptical about everything that we do and figure out new ways of carrying out experiments to learn what works better in every sphere of our work. This is me just showing off. This is a quote from Forrester a few years ago. If agile software development was the opening act to a great performance, continuous delivery is the headliner. I think what we're talking about here is kind of a leading edge of what we know as the best of software development process at the moment. So let's quickly whiz through an example of this. So we have some developers working on a change. They're going to submit the change to a version control system of some kind, and we're going to have a system that's monitoring the version control system, and every time there's a change, we're going to evaluate that change. This sound familiar? This is continuous integration. Okay? So continuous delivery kind of is in part based on continuous integration. So what we want from this is we want to fail fast. We want, if this change is a bad change, we'd like to know about that as quickly as possible. Now, the best possible way that we can know about that is that when we're a developer, we get a little red squiggly line underneath the change in our IDE. The second best to that is that when we run some tests, they're going to give us an answer back. I generally recommend, this isn't always possible depending on your technology and your problem, but I generally recommend that you aim to get this feedback cycle in the order of about 5 minutes. If you do the job well, you can run tens of thousands of unit tests and a build in about 5 minutes. If you do the job badly, it's hard to do. But that's kind of the goal. The reason for that is kind of psychology. We want these people to be able to make a change and wait for the result. If you go much over 5 minutes, certainly if you go much over 10 minutes, what tends to happen is that it's slow enough that it changes the way that people work. It means that people will commit changes less frequently. And instead of working in lots of small little packets of change, you start storing up bigger units of change, and you end up kind of working for a whole iteration or maybe a few months before you commit a change. And that's a risky, difficult thing that kind of compromises our ability to see what's going on. It's kind of counter to continuous integration. If the developers commit this change and all looks good, they can now move on and start doing something else. Here's where we start to diverge from regular continuous integration practice. Now, we've just compiled and built some software and we just run a whole bunch of tests against that software. We'd like those results to be useful in the future. A common practice in many organizations is that even if they're using automated testing, is that they'll do this and then they'll throw that build away, and the next time they want to deploy it into production, they'll rebuild the code. And the downside with that is if you use a different version of the compiler, or if you link with a different library, maybe you introduce a problem that would have been caught by these tests. So we're not now testing the same thing. So we'd like to be able to store the results of this build, the thing that we're going to deploy into production, and that will be the thing that is deployed into production if this release candidate makes it all the way through the rest of the validation. So we're going to store the results of the build, the deployable artifacts, in a thing called an artifact repository. There are few stronger advocates for test-driven development in the world, I think, than me. I'm a big fan. And the commit test stage is largely, in my mind, to do with the result. You're running the results of test-driven development. Now, test-driven development is a wonderful thing that improves the quality of your software without a shred of doubt, in my opinion. Not because of the testing, but because of the impact it has on the way that you design code. It applies a pressure for more loosely coupled modular systems with a good separation of concerns. That up until test-driven development, the only pressure that existed for that was the integrity and experience of a good software developer. And we add to that integrity and experience the demands of test-driven development, which requires testable software is modular, is loosely coupled, and has a clear separation of concerns, because that's how you make it testable. The downside is that, or the limitation is that it asserts that the code does what the developers think the code should do. That's not the same thing as saying doing what the users need it to do. So we need another dimension, another kind of test to evaluate the system, and in continuous delivery terms we call that acceptance testing. Now we want to exercise the system from the perspective of an external user of the system in lifelike circumstances. I think that using human beings for any form of regression testing is costly, slow, low quality, and a waste of human beings. I think that we thank you. I think that we should be looking to use automation for that. We should automate all of our regression testing, and we use human beings for the clever things. We use human beings for the exploratory testing and figuring out whether the software paints pretty pictures in their heads when they use it that makes them extrapolate what to do next and all that kind of stuff. So we use human beings as part of the process, but not for regression testing. Performance testing, if we understand that the software does what the developers think it ought to do, it now does what the users want to do, it paints pretty pictures in people's heads, we want to make sure that it works quickly enough to be able to give us useful, usable results. So different levels of performance testing. As we're going through the process, we're building up tags of metadata about what's happened to this software. We want to be able to make sure that the software works when we deploy it into production with the data that will be in production. So we could evaluate that it works with production, a cut of production data. What we used to do on the project that was the basis of this, is every morning we'd take a cut of production data, we'd anonymize it because this was a finance application, and then we'd start the application up, run any data deltas to our database, migrate the data set, start the system up, and run a few simple smoke tests to see if it still behaved and was sane. At this point, we've now built up this fairly comprehensive picture of the behavior of our system. So the only decision is, should we release it into production? And the only basis of that decision is, has it passed all the tests? Yeah, okay. It's passed all the tests, let's go. The other slight constraint on that choice, as I said before, is it may not make sense for your business to automatically push this out into production, but working in a way so that our software is always in a releasable state gives us the option, gives us the choice. So at LMAX, the place that was the basis, the place where we built the financial exchange, the cycle time of 57 minutes, the source of this particular deployment pipeline, we would release every weekend by default. We could release every 57 minutes, but we didn't because it would slow down the system and it would change somebody's trading experience if we deployed our system live. So we didn't do that. But we could have. If there was a problem, we could have released after 57 minutes. So we can push the change out into production. This whole mechanism is called a deployment pipeline, and it's kind of one of the core ideas of continuous delivery. And the idea is essentially it's a branch prediction algorithm. What's going on here is that the developers at the start are betting that the 5 minutes that they spend waiting for the commit results are going to tell them that most of the time, if it passes there, it's going to be okay through the rest of the pipeline. And then it's going to take roughly, 49 minutes to do the rest of the pipeline on the whole, in the LMAX example. So I generally suggest to people that you should be looking, the ideal shape is to do this in under about an hour. So looking to optimize this whole cycle to get that kind of right. So some of these stages are working in parallel and some of them are not. But at the end, if a failure happens later in the process, the developers have lost their bet. Now they've got to drop whatever it is that they're doing, they've got to go and fix the problems that they've just introduced. And so they lost their bet. If it all passes, they've won their bet, and while all of that other evaluation was happening, they've just gone and done some new work and have probably committed it and started the cycle again. So one of the pushbacks that I sometimes get for this is, okay, that sounds really nice. It's a really nice rational description of how software development ought to work, and I'm sure it's great for small projects, but my project's quite big and complex. So Google is my answer to that. Google have made the unusual choice of putting all of their software into one repository. Oops. Okay. Is that me walking around? So they put all of their software into a single repository. All of the different projects, Chrome, Gmail, all of those things are a single repository, and any commit to any of those projects triggers the build and evaluation of all of them. They've invested massively in hardware and software to make this efficient. And they do, this data is about 2 years out of date. I have no idea where they're at now, but the numbers are significantly bigger than these numbers. But 2 years ago, they were doing 60 million builds a year and growing exponentially, 100 million lines of code. Tests are run on every single commit, and there are more than 20 commits a minute. And there are 100 million test cases executed every day. So if your project is bigger than that, maybe continuous delivery doesn't scale. Otherwise, and if it is bigger than that, come and talk to me, I'm interested. The other pushback that I get sometimes is, you want to push out how many times? you want to automate the deployment into production? Are you insane? Our deployments into production are absolutely nightmare. This is so risky, you just must be crazy. So for that, my answer is the Amazon build process. Could I have a show of hands of people that have used Amazon in the last couple of weeks? Okay, which version did you use? It's a stupid question because on average, once every 11.6 seconds, Amazon changes. And on average, once every 11.6 seconds, a change is deployed to 10,000 servers. Since they've done this, they've seen a dramatic reduction in outages caused by deployments. Because you have to, if you're pushing changes out once every 11.6 seconds, you've got to be pretty good at deploying. They've seen a massive reduction in the amount of time they spent recovering from failures, and less than 1 in 1,000 deployments causes any problem anyway. And when it does, they have an instantaneous rollback because each change is going to be tiny. Each change is going to be small. So it's easy to discard it if it's not working. This process dramatically de-risks release. So this is a much safer approach. You can kind of think of it as kind of smearing the risk out over time. So instead of bundling up all of our risk into one 103-day cycle, we break it down into lots and lots of little pieces until each little chunk of risk is tiny, and so we can afford it. The last pushback I sometimes get is, okay, so it's easy for the web companies. After all, what's Google and Amazon? They're just websites, right? But my technology is way too complex to do this kind of stupid thing. And my example for that is HP LaserJet. So the HP LaserJet team, this is a fascinating example, which is talked about in a book that I'm going to recommend to you in a minute. And back in 2008, they were in a sorry state, so they did an audit of where they spent their time, and this is the results. So they were spending 5% of their global development effort on innovation, by which they mean any new feature. This isn't hard, detailed research. This is just building a new feature. The situation was so bad, they had a 5-year backlog for development, and the business had literally stopped asking them for anything new because they knew that they would never get it. They spent 25% of their effort, 5 times as much as they spent doing new features, porting code. That's because they had one repository, and each device, each LaserJet device, had a separate branch. So anytime anybody made a change in one of them that they thought was good, they'd then have to go and port it to all of the rest. 5 times as much as they spent doing new things, porting code. 5 times as much as they spent doing new things on support, which probably says something about the quality of the software. They were in this horrible place, and they decided to do kind of what we've just done and gone back to first principles and kind of figured out how to move forwards. And they kind of independently came up to the same conclusions. So after they'd adopted this new engineering approach, they're now spending 40% of their total development effort on doing new things, 8 times as much as they were doing previously. And yes, they spend an awful lot of time, money, and effort on writing tests, automated testing, improving tools, agile planning, continuous integration. A large proportion of their effort is spent on that. But the results are talk for themselves. So afterwards, their development costs were reduced by 40%, programs and development up by 140%, development costs per program down by 70%, and resources driving innovation were up by a factor of 5, actually a factor of 8. I'm not quite sure that's right. This is described in the book that's up here, Large-Scale Agile Development. It's a nice, easy read. It's more about the organizational change than it is about the tech, but it's an interesting read. It's my argument that continuous delivery changes the economics of software development for the better. And fascinatingly, we're starting to get research that backs me up. There's peer-reviewed data for the first time in the history of software development process that says if you practice this style of development, the organization that you practice it in is more likely to make money. That's staggering. We've never had anything like that before. Oh, I'm missing one. That's a shame. So the slide that I'm missing from this version of the deck says that The slide that I'm missing from this, the slide that I'm missing says that if you do this, you're twice as likely to exceed growth targets or monetary targets over a 2-year period. You're 66% more likely to improve the quality of your code, and I can't remember the last one. So here are some of the organizations that practice continuous delivery. And there are the usual suspects. There are the people that you would expect in here. Some, Google, Amazon, Stack Overflow, those sorts of places. But I think there are some surprising organizations in here. The first time that I saw SAP were talking about continuous delivery surprised me. I've always thought of SAP as kind of a definition of a legacy system, to be honest. But they are reporting some amazing improvements in the quality of their work by practicing this in some divisions. I was particularly proud when I found out that the Curiosity rover from NASA, that amazing piece of engineering that landed the rover on the surface of Mars from a rocket-powered sled lowered by a crane, the software that drove all of that was developed using continuous delivery principles. Because there was no way that there was no redundancy, either it had to work, so they had to test it very thoroughly. This is a tiny sample. There are organizations across the world of all sizes that are doing this, and they're seeing dramatic improvements in the quality of their work, the joy that their employees have in performing it, and the delight that their customers have in the software. Thank you very much.